and has co-founded 3 spin-off company, Pix 4D, Full Vision, and Neuroconcept. He will give us a valuable talk today on deep 3D surface mesh.
Thank you.
Please, we can.
So good morning. So as has just been pointed out, I have been reconstructing surfaces for a few years, deep all the way to the dark ages when deep learning was not known or not widely known. And here's an example of something we did about 10 years ago, which is you sent unfortunate PhD students to top Matterhorn. They launch a drone. The drone captures a bunch of images, and from this you build a 3D model. So in fact, this is really old technology. This has been around for a long, long time. What was new in 2010 or 11 was that this process was now fully automated, up to the point where really the only manual intervention was the launching of the drone. And that turned out into one of these companies that was mentioned, that's called Pix 4D, that is actually has become now a standard for mapping. And actually for the PhD students, the younger people, there was not a shred of deep learning in this. And it worked quite well. But one of the problems, I mean, it's not a problem, is Matterhorn does not deform really quickly, at least not on a human time scale. So we've also worked on deforming surfaces. So I'm sorry, I mean, I should have a cricket sequence, but all I have is baseball. So what this is a baseball that's being shot at something that simulates a bat. And the point here is to study the shock. There's a collaboration with colleagues at Washington State University who are mechanical engineers, and they want to understand the physics of the collision. And the problem is that it's actually complicated. And writing good simulation code is non-trivial. And what our job was to observe this with a fast camera. In each sequence, we had a model of the undeformed ball. We could project it into the image, project it and deform it so that it projects at the right place in the image. From this, we can infer the 3D and reconstruct what happened. And so it was actually interesting because our role as vision people was to provide the ground truth so that we can tell the mechanical engineers, here is what happens for real. Your simulation codes should reproduce that. And so that was a fun project. And both of these things I've just shown were depended on 3D surfaces modeled as triangulated meshes, which is an excellent representation. It's widely used. It's been widely used for a long time. It probably will be widely used for another long time because it allows you to do a lot of very accurate computations. So that's nice. However, there are a few limitations. One is that the topology is fixed typically. So they've been algorithms to change topology as you deform, but they're kind of hacky. It's hard to make work. And they are not all that deep learning friendly. So in 2011, it didn't matter. In 2022, it does matter. So there is another very nice representation of surfaces. Instead of having explicit 3D meshes, you can have implicit surfaces. So the basic idea of an implicit surface is you put the object you want to model into a box, a 3D cube, and you define a function from R cube to R, which can be either positive or negative, and the surface is implicitly defined as the place where you transition from minus to plus. It's a zero crossing. And one of the very nice properties of this is that with this representation, you can change topology in a completely differentiable way very easily. And that's, again, like deep learning, actually, this is not a new idea. The idea has been around since the 1990s, at least. It's what's called level set for those who remember. It had a problem, though, and I'm going to come back to this, which is it didn't catch on in the 1990s because if you have to represent this cube and you represent it explicitly, you need an awful lot of memory to represent anything at a sufficient resolution. And that was, and it still is, a problem. Okay, so let's look at this a little bit closer. So formally, you want to model the standard SIGGRAPH rabbit. What you're going to do is define a function f from R cube into R, which is negative inside, so it's blue on the image, positive outside, and 0 on the surface of the rabbit. The image here is 2D because it's easier to show, but really it's in 3D. And a very good one is that that function can be what's called a signed distance function, SDF, which is the normal Euclidean distance, except you add a sign. You make it positive outside, negative inside. And so that means that by changing f, the value of the field, you can change the shape and the topology. Nice. But what is not so nice, or what was not so nice, is the fact that how do you represent f? You need this cube to give its values, and that's memory intensive and unpleasant. Well, at the end of the Dark Ages, in the modern era, deep learning has happened. And there are some bright people who figured out, so it's about 3 years, that, oh, you don't need to represent the cube. You can use a deep net for that. So instead of explicitly having the values of f, what you do is you have a deep net that takes a point in space, x bold, takes that as input, outputs a value, and that value is the function f that defines your shape, and theta on the slides are the weights of the network, and that essentially defines the shape. If you change theta, you change f, and therefore you change the shape. Okay, and then you can do even a bit better than that. You can actually condition the output of the network on a code. It's called C on the slide, which means that the value of f is now conditional on C. So C is an input to the network. For all points x, you use the same C, which essentially means that the vector C is a latent vector that defines the shape. It's the parameters that control the shape. And later in the talk, we'll see that we optimize with respect to C to change the shape. Great. With one small problem remaining is that if you happen to need an explicit representation, a mesh, for example, because you want to do rendering, or as we'll see later, because you want to do computational fluid dynamics, you need a triangulated mesh at some point. And the standard algorithm to do this is marching cubes, or variation of it, which will go into that 3D space and produce triangulations. So it's a very good algorithm, works well, but it's not differentiable. And it can kind of slow too. And that's a problem, because if you're going to put this into some kind of a end-to-end trainable pipeline, having a step that's not differentiable is a showstopper. But it turns out, and that's one of the things we've been working on, is it actually is not an issue. So why is it not an issue? Well, let's look at what you do when you train a deep network. So typically, let's assume you have a loss function L that depends on an explicit representation as defined by some vertices V and some facets F. So that could be, for example, you do a rendering and then you compare the rendering to an image. That clearly depends on V and F. Okay, so when you compute the forward pass, you have to evaluate L from your implicit field, S. So you take S, you run marching cube, it's called MC on my slide. You get V and F, and then you feed that to the loss function and you get your loss. So the forward pass is not an issue. What is an issue is a backward pass. So when you train, you want to compute gradients, you need to compute the derivative of L with respect to C, where C is this latent vector I've mentioned, which means, so let's write the chain rules. It's a sum of these three terms that you see. And two of them are normally easily differentiable, which is dl over dv, which is the derivative of the loss with respect to the position of vertices. Usually this is a differentiable function. ds over dc, well, S is the output of a deep network, that's differentiable. The problem is the one in the middle, this one. This one is the output of marching cube, the vertex, and that is not differentiable. Okay, so, well, yes, but F is supposed to be a sine function. So you can actually prove that if S, a point on the surface, you take V, I'm sorry, to be a point on the surface on the zero crossing, and you do an infinitesimal change in S, you can prove that actually V is going to move by the normal to the surface, which makes sense. And that normal in the case of an SDF is just minus the gradient. So marching cube is not differentiable, but you can still compute the derivative of the samples on the surface. So you're happy. And actually, it's more general than that. This result applies to any sufficiently smooth function F. So for example, if you prefer occupancy grades to SDFs, that's fine. The result still holds, except you need a slightly more complicated formula. You need to normalize by the gradient of S that you see in the denominator. And these two formulas, of course, are consistent because when S is a signed distance function, gradient of S, the norm of gradient of S is 1, and you find the second to last formula. Okay, so what this means is that we can go from a code C to a triangulated surface in a completely differentiable way. So let's say we start from a sphere on the left with some code C0, and we want to transform it into a donut. So why a donut? Because I changed topology. One is genus 0, the other is genus 1. And to do that, so for example, let's say we have a cloud of points and it's being attracted to that cloud of points in the shape of a donut. So you start with a deep SDF code at C0. You use marching cubes to find points on the surface. With the formulas I've shown, you can do both the forward and the backward pass. So compute the function and its derivatives. You use a gradient to update C, and you iterate. So in this manner, for example, you can start with this genus 0 cow and turn it differentiably into this genus 1, meaning with one hole, duck. Okay, so yes, before I move on, one limitation I have not mentioned is that SDFs and occupancy grids and all these things are only good for watertight surfaces. There has to be a clear inside, outside. An open flat surface, it's not trivial to represent. I mean, it can be done, and the way you typically do it is you put an inflated SDF around the open surface. That works, but it tends to lose precision because you have to make it relatively thick. So what we have been doing recently is to extend this approach to open surfaces. So for example, the shirts and the pants. So the body here is a simple body that's normal implicit surfaces. But on top of it, we have the shirt and the pants that are open surfaces. And what we've done is we've replaced the SDF, the signed distance function, by a UDF, an unsigned distance function. So unsigned distance function is just distance, I mean, without the plus or the minus. And when you represent a surface like this, the place where the surface is not the zero crossing, it's the place where the function reaches zero. And that creates a difficulty, which is the marching cube algorithm is designed for things that have zero crossings. It doesn't work on UDFs. So what we did is to adapt it based on the following intuition is you have a function that has some value, it decreases, it gets to zero, and it increases again. At some point, the gradients are going to be oriented one direction, and as you reach zero, they're going to flip. So the surface is where the gradients on both sides of a point in different directions. So what we've done is adapt marching cube to take advantage of that intuition, and that's what you see on that video. And the rest of the mathematical reasoning is the same. The derivatives can still be computed, and everything I've said remains true. Okay, so that was kind of the theory behind what we've been doing. Are there any questions at this point? Because I can answer them. The question, we'll leave the question for the end. Okay, fine. So let's now say how we can use this. So the first use is single view reconstruction. So why do we do single view reconstruction, by the way? I mean, we can have multiple views. If you have my personal opinion is if you want to reconstruct something, take multiple views. But CVPR, BMVC, ICCV reviewers do not necessarily agree. Therefore, we do single view reconstruction. So let's say we want to do cars. So the first thing is going to train a network to generate cars. We need this this network. So we take, say, ShapeNet, the cars, and we train an encoder decoder to produce cars. And what this gives us is a generative model, because once we've trained the decoder, we have something that we can use as a generative model. We can put a code C, we put it in our decoder, it will, and we will render it. And what we want, we can optimize with respect to C so that the rendered image looks like the original one. So this can be used in two different ways, either in a discriminative way where you feed an image, it outputs a code. And then in a generative way, you have code and now you refine it by optimization. So here's an example on a chair. So of course, it's been now the encoder has been trained to produce chairs. We give it this image. The first step, which is a discriminative step, produces code that's kind of rough. So it gives you something that's more or less correct, but not all that precise. And then you optimize. So you use essentially the math I've just shown to optimize C so that in the end, the rendered image, the fourth black image, looks like the original one. To show you that it's reasonable, I have on the right two 3D rendering. One is from the same viewpoint, the other from a different viewpoint, and you can tell that the chair has been reasonably recovered, even though it has these very thin legs, which are not that trivial to handle. And now we can also do the same thing. So we can do this for chairs, we can do this for cars, and we can also train it to do reconstruction, not from images, but from sketches, which is what you see here. And that's actually a potentially useful tool for, say, an artist who likes to sketch things in 2D and produce directly the 3D without having to go through a CAD modeling system. And moreover, you can now play, once you have this, you can play games. You can say, oh, well, I have this car and well, the back is too long or the wheel is too far back. Change it. And the way to change this is you sketch in 2D a different back and a different position of the wheel, and the thing will adapt it. Okay, so that's one application. That's what I would refer to as the BMVC/ICCV/CVPR application. And here now I would like to show a real application, what we really want to use this for. And what we really want to use it for is shape optimization. So in my career, I've done a lot of shape reconstruction until I had this bright PhD students are really great, but this great idea, say, aha, we can use it not only for reconstruction, we can also use it for optimization of the shape. By which I mean, let us say you are now a car designer, you work for some car company, and you want to design the best car you can. So that may mean, in terms of aerodynamics, means that it has low drag and a lot of downforce that will glue it to the road. So the way you typically do this, you start with your CAD system, you design your car, you run a simulation. Well, actually, no, you design your car, you send it to the office, they run the simulation, it comes back. Normally, the first try is, I mean, there are things that are not right. You do it again, and you do this back and forth, and it works, but it's slow and expensive. So there has been a lot of interest in that community, in the CFD community, for automating this. And a standard technique is known as kriging. I call it Gaussian. I mean, I remember talking to Raquel Otasun and using this word, and I got SGP, of course, it's Gaussian processes. And the idea is you have a bunch of example shapes that are more or less examples of the cars, say a bunch of cars, and you run your favorite CFD simulator. It doesn't matter which one it is, the one you like. It will produce some results, which is what I'm showing here. The idea, the colors at the bottom are pressure fields. At every point, you can compute the pressure, and from that, you can compute things like drag and lift and everything you need to know. And then, having done this, you are going to do nonlinear optimization, interpolation, by which I mean, let's say we are interested in minimizing drag. So all the little red boxes on the right are one simulation. So for that particular shape, that particular choice of shape parameters, I get a value of the drag. Oops. So now that I have done this, I can actually fit a surface to this. It's called a response surface. And that surface, I can try to find a global optimum, a global minimum. And because it's all differentiable, I can use standard optimization tools. And how do you get a nonlinear interpolation? Well, the traditional way is to use a Gaussian process, which is what I said, that Kriging and Gaussian processes are the same thing. You use a Gaussian process and you do your minimization. So that works as long as your model does not have too many parameters. So typically Gaussian processes beyond dimensions of 30, 40, they start to choke. And one of the reasons, I mean, my understanding is why that happens is Gaussian processes depend on computing distances between samples. When you are in a very high dimensional space, everything becomes very far from everything else, and you lose, it doesn't work anymore. Okay, so that's a problem, but there are other nonlinear interpolators. They are known as CNNs, because that's really what they are. They are nonlinear interpolators. And more specifically, GCNN as in geodesic convolutional neural networks, because normal CNNs operate on images, GCNNs operate on graphs. It's the same principle. You do convolutions, you have your value, that of your neighbor, you compute weighted averages or convolutions, but you do it on the graph. And the graph in this case is going to be the triangulated mesh that represent the object you want to optimize. And that actually works quite well. And the big advantage in this context of CNNs is that they will eat virtually unlimited number of parameters. You're not limited to 30 or 40. You can essentially go as high as you want. So you can be much more general. So the specific GCNN we use is something like this. I'm not sure, the architecture is not essential, but basically it's a ResNet with a few additional tricks. The one trick that is important is that it helps greatly to make it learn several things. So say you want to compute for a wing. What the quantities that you're really interested in are the drag and the lift, two numbers. But it helps to make it compute pressures at every vertex as well, even though you could say you don't really need them. But that's an experimental observation. It looks like forcing it to learn the pressures also forces it to learn a bit of the physics, which means we have observed that the generalization behavior is much better if we do that. So what that gives us is a deep net once it's trained, that you have here a bunch of cars from ShapeNet. You can run, well, actually a cleaned up version of ShapeNet. Must warn you that if you're interested, that we will make it public. The original ShapeNet is kind of messy, and the CFD computation don't work very well, so we actually cleaned it up. So on this cleaned up ShapeNet data set, we can run a good simulator. It takes a long time, but we get results. And we compare this to what our emulator, the CNN, does, and it's very, very close. So I'm going to call it D, and I'll use it again. And here's another example with planes this time, where we have a collaboration with Airbus, and they wanted to know what we could do on their aircraft. And on the left, you have, so this is half of an Airbus. You can run a full simulation, which gives the result you see. Again, the color as the pressures. And what our emulation does, and it's very, very close, but one takes an hour and the other takes 30 milliseconds. So that's interesting, because if you can estimate these things very fast, you can explore more of the shape space. And even more importantly than that, you have something that's differentiable. So now the drag, this operator D I've called, takes as input the vertices of the mesh and outputs a drag. And because it's differentiable, we can actually optimize with respect to the shape parameter, with respect to the mesh, to, in this case, what this is you take a sphere, and that sphere is incompressible, and we are going to build a shell around that sphere to make it more aerodynamic. And what you see is the shell it comes up with this long tail, which actually makes sense. I mean, for those of you who ever watched speed racing, bicycle speed racing, they have these very long pointy helmets at the back. Same reason. You can do this on something that flies. In this case, it's a drone. This is a plane drone from a company called SenseFly, which is an offshoot of one of EPFL's robotics group. And these people are roboticists, therefore they really invested their effort in designing a good autopilot. But they didn't spend much time designing the wing itself. The wing is a very basic, simple shape, which means it flies, it consumes, it needs more power to stay in the air than if the wing were more efficient. So we've been looking at this. So this is a drone you can buy. It has the performance of an aircraft is often given as what's called the lift over drag ratio. So L over D. You can use our approach to reshape the wings to make them more efficient, or you can actually go one step further and reshape both the wings and the fuselage so that the fuselage contributes to lift. And it's actually even more efficient. And this is a relatively simple constraint optimization problem, because of course you optimize under a certain number of constraints, which is you need a bit of space to put the camera, the motor, and everything else. Here's another example of something similar with a boat this time. So what this is there used to be a student competition at EPFL where every team would be given the same electric motor, and the goal was to build a boat that could go around the course as fast as possible. And all these boats, this is one entry, and all these boats were what's called foilers. They are foils that lift them out of the water. And sorry for the people watching remotely with these points. This is what it is. What you see, this thing is, you've seen aircraft with two tails. No, it's the same, except the tail, the wing is underwater, you don't see it. And it's what's lifting the boat out of the water. So that wing needs to provide enough lift to get the boat out of the water so it doesn't drag. But at the same time, it needs to have low drag to do this so that you can go fast. And you want good stability, because you have an autopilot and you have ailerons on that wing, but every time you use them, you actually create drag and slow down the boat. So the less you use them, the better. So this is, again, an optimization problem. We have a loss, this function L I mentioned a while ago, that you want to minimize to achieve this. And here is the optimization is going on. So what you're looking at is actually half of the wing. You have to imagine that this is the left part of the wing. There's a right part that's symmetric, and the whole thing is a wing underwater. And what it's doing, I think, is interesting, because to me, this doesn't really look like a wing. Wings don't have this kind of wide spoon at the end normally. But what have I asked the network to do? I have asked it to give me low drag and good stability. Well, now if you think about it, if you want good stability, it's not unreasonable to make the end a little bit wider to do that. And I think this example is very cute because coming up with a shape is not necessarily something I, as a designer, would have thought about. It came up because it explores a lot of the search space. On occasions, it comes up with unexpected solutions, which are actually good. And you might, once you look at the result, you say, oh, yeah, it makes sense. But it's not obvious that you would have done this by yourself without the help of the optimizer. Okay, so these were actually simulation. We don't really build this, but this we built. So this was a collaboration with a school in France, Nancy. And what this object is, it's a bicycle. Doesn't look like one, but it is a bicycle. And more specifically, it's a shell, the aero shell of a reclining bicycle. So the finished product is this. You have, you see the white shell. You see, these are the wheels. And these are the clickers. And when they use it, they are reclining. So feet here, head here, and seat. And actually it's funny because there's no window. So they are looking out through a camera. And so the game was, that was just before COVID. They went to Nevada, a very long, 5-mile long road, straight and flat. So you pedal as fast as you can, and you get clocked on the last 100 meters. And they ended up going fast. So 136 kilometers an hour on, there's no electricity here. It's just pure muscle power. So these guys are strong, yes, but it did help quite a lot that they had low drag. So that was an early proof concept that I can write equations, but hey, we can actually make it work. So in the examples I have shown, the optimization was done with respect to the vertices of the shape. So really there was, I don't remember how many vertices there were in the mesh, but the number of variables were 3 times that, which is a CNN. Again, a GSCNN can do that. But in some cases, you might want to have a prior, which is what I've talked about. You can train an auto decoder, in this case, to produce car. And you want to constrain the shape you get to be car shapes. So we've done this. So we have this auto encoder, this encoder that you give it a vector C, it produces S of C, which is a car shape thing. And then you feed that to D, the thing that computes drag. And now you have a function, a differential function, that D of C, that gives you the drag that corresponds to a particular latent code. And you can optimize with respect to this. So here it is. You start with an ugly SUV, and you optimize C, and you get a no less ugly SUV, but it is far more aerodynamically efficient. That's something. Of course, the concept of an aerodynamically efficient SUV is a bit weird, but whatever. And that actually has real application. So we actually have a little spin-off company called Neural Concept that tries to commercialize these things. And with this, we've actually built this tool that combines some of the things I've shown, which is in a car company, you typically will have a group of people who are called designers, who are not They don't really know that much about physics, but they do know about making cars look good. They're artists, essentially. And they like to sketch. So here's a tool where they can sketch a car on an iPad. And the system, will essentially fit one of these models to the sketch, and at the same time, try to make it aerodynamic. It will find the best compromise it can between it looking like the sketch and being aerodynamic. And that's actually useful for people, these designers, so that every time they do a sketch, they don't have to wait 3 weeks for the simulation bureau to do the simulation. It's instant. Okay, so that's kind of where we are right now. So now I'd like to conclude to present a few what's happening now, what's happening next. The shapes I presented with these SDFs and UDFs, essentially we model the whole object as one single surface, watertight or not. But if you think of a car, or any industrial object, it's usually more complicated than that. In a car, you're going to have the car body, and then you have to have the wheels and the rear view mirrors. And so one thing we've been developing is a more sophisticated representation where we can combine the free-form surfaces style with shape, more traditional CAD primitives. The wheels are going to be round. We know that. And we want to put that, and we can represent them as simpler primitives. So we have a system that does this, where the latent vector now, it's still there, the vector C, but it produces both the car shape and the parameters for the primitives. And that's actually turns out to be useful because it means we can now do our optimization, but preserve the fact that the wheels are round and our body, because otherwise it doesn't go. Because if you see a lot of the papers that on ShapeNet, I mean, the wheels and the body are joined. You can't build that. So that's a stab at going towards a representation that in the end, you can actually build it. And here's an example on what's called a water mixer. So a water mixer is an industrial part where you have a kind of a tube. At one end, you put several different liquids. It goes through the helix in the center that's turning, and it's mixed. So it's homogeneous. And we've designed one, and that's actually a combination of one of these SDF surface, the helix, which has a complicated shape that can change, and simpler primitives, the tube in which it is, and the screws at both ends. And because we have this unified representation, we can deform one of these things and everything remains consistent. So this becomes hopefully a useful design tool. It also could be a tool for vision because it's a generative model. You could fit it to the data. It's going to be very specialized, but within its specialty, it'll be very robust. And the final thing we are working on is I mentioned planes. So we're actually designing one now. And the plane was, so designing, a real, a jet is complicated, expensive, will take 20 years. I don't have 20 years. So what we are going to do is something a bit simpler, which is a glider. So the plane you see on the right. And so it's a plane, but it does not have an engine. And what it's going to do is something called dynamic soaring. And dynamic soaring is a kind of flying where you go to a place where you have a mountain and the wind is blowing from here. If you are below the mountain, there's no wind because you are shielded from the mountain. above the ridge of the mountain is a lot of wind. So there is what's called a wind shear here, where you have a transition from calm air to fast moving air. And it turns out that if you do ellipses like this, you go upwind mostly at a place where there is no wind, and you go downwind at the place where there is a lot of wind, you're being pushed. And what this does is it steals energies from the wind. And this plane, even though it doesn't have an engine, is being accelerated every turn. You get a little bit more energy, you go faster. And today, the current world record for this is 882 kilometers an hour. That's over 500 miles. That's already in the Mach point something range. It's really fast. And of course, as always, people want to go even faster. And so, I mean, that, I don't know if that number means anything to you, but this thing is moving at 300 meters a second, almost. That's a lot. And the current ones are remote controlled. There's a guy standing on top of the mountain with a joystick, but you are getting to speeds where it's becoming increasingly difficult. The humans are just not fast enough. So, and another thing that's important, this really makes this problem amusing, is when you go through the wind shear, there's a lot of turbulence. So you really have to control it. So what's the solution? Well, it's to make it a drone. We're going to turn it into a robot that will control itself. And we have to design it so that control is relatively easy. And the idea here is, if we want to go fast, we want this bit, same idea as the boat. We want as little deflection of the controls as we can, because every time you deflect the control surface, you slow it down. So, turns out that this can be written, so I'm not going to go into the details, but there is control theory, there is, you have what's called a control law, you have a tradition you want to follow, and the standard control is to design, you have a criterion, and you to compute your controls so that you follow the desired trajectory given the shape that you're given. What we want to do, and that's just at this point, it's just an equation, there is nothing behind it, is to go further and to design the shape so that control is easy. Which means we are going to optimize something that's a weighted average of the control, the usual control equation, and the losses I've been talking about. And because all of this is differentiable, all of this is differentiable function, you can just create this this new loss function. And in the end, in theory at least, you can optimize both for performance and controllability. And that's what we are now working on. Okay, so if you re-invite me in 5 years, I'll tell you more. And so in conclusion, what I've shown is that you can combine implicit, explicit representations in a very seamless way, so that you can exploit the strength of both representations. And deep signed, unsigned distance functions are a very good way to do this. And finally, which was the last slide, this formalism can be extended not only to shape, but also to control. And this actually, I think, matters because there are lots, I mean, all modern machines need this. They need to be performant, sustainable, and easy to control. So cars are an example. This is another one. This is another crazy project that's going on at TPFL, which is to have to break a speed record, a sailing speed record with this is a sailboat. Looks like a rocket, but really it is a sailboat on foils. And the idea is to go 80 knots. And maybe more mundane things like electric motors, battery cooling plates, and any number of other modern contraptions. And so our long-term goal is to disrupt or to change the way computer assisted engineering is done so that you don't do things in, many different separate steps. We have one, the holy grail end-to-end trainable pipeline to do everything. And we actually, of course, as I said, we are writing papers, but we also have a little spin-off company, and we're trying to use both to change the world. And that's it. Thank you very much.
Thank you so much for the very interesting presentation. As coming from aerospace, I found it really interesting. And I saw how you were trying to basically estimate the pressure field from changes in shape, which is very fascinating. What I'm wondering is sometimes changes in shape can change the physics underlying in the flow. For example, the flow can go from laminar to turbulent, or if you're talking about some solid, you can have shock waves that are changing the physics completely. So have you actually tried to deal with this kind of issue with your model? And do you think the model is actually able to estimate these changes in physics?
Yeah, we are trying, we are sweating, but it can be done. So yes, I mean, from my point of view, I'm a computer scientist, I'm not an aerodynamicist. All this is black magic. And we have a research engineer who's an aerodynamicist. And basically dealing with deep nets is garbage in, garbage out. So they're only as good as the training data. So your training data must reflect all this, which means the parameters you use in your simulation and the turbulence models and all that have to be chosen just right. So the short answer is yes, we do, but it's not easy.
And maybe a slightly more elaborate answer is we are now for this glider I'm showing you, we are getting wind tunnel data. And it's better, but it's not perfect because of the walls. So we want to, and then we are going eventually to get flight testing in the air. And what it's going to mean that eventually we'll get a pyramid of data to train our network. So flight test is probably the best, but we won't have much of it. Wind tunnel will have some of it. It's not quite as good, but it's quite good. And then a lot of simulation data. And the problem to address this issue is how do we use the good, it's a generic problem is how do you train a deep net with heterogeneous training data of different qualities? And that's talk to me in 5 years. But we are really looking at this.
Thank you.
Hello. Also, I want to follow on the previous question on your answer. Because you will not have this high quality data, for example, for doing student designs. So how to balance between kind of exploring the cube shapes and sort of getting good data for because we will not use a square wave line.
So the short answer is evaluation optimization. The longer answer is one of the problems we can get good data close to the shapes.
Oh, sorry. We can get good data for the close to the shape we already have. What we've experienced is as we start optimizing, we move away from the training set and the prediction start degrading. then what you have to do in real life is when your predictions are not reliable anymore, you have to retrain. So the way we think about this is we have a simulation budget. I mean, I know we can do 1,000. So you do 500 initially to get things going, and then you use the other 500 in an active learning fashion during optimization. But then the key is to be able to know when your predictions are not accurate anymore, which is one of the big problems of deep learning. So it's funny because this is a very applied problem, but you get into all the fundamental issues are all showing up. And so that's another, probably don't have time to talk about this, but we are actually actively working on trying to estimate the uncertainty of our network so that we can do the retraining.
Fascinating, so thank you very much. I was looking at what you were presenting and thinking, will the cars of there is in the future saying, okay, it's raining, so I'm going to deform my design and become a little bit different given the circumstances. There's now side wind, so the actual shape will optimize real time. Is that even possible? And also, are we going to discover something different? Are we going to realize we shouldn't have 4 wheels or we shouldn't have 2 wings? Is that even feasible?
I hope so. I can't prove it, but that's why I like this little example of the wing with little, the wide paddle at the end, which shows that occasionally it goes in directions you wouldn't expect. So if what I just said, if you follow it in that direction, say, aha, it likes this kind of this corner of the shape space, for which usually it hasn't been trained because it's unexpected. Then you have to retrain a bit. So this is really not about getting rid of simulation. Simulation is and will remain an important tool, but it's a way to use your simulation budget more efficiently to go further out in the shape space. Now, of course, we run into the problem that deep nets are better at interpolating than they are extrapolating, and that's another fundamental problem we are going to have to contend with.
I was just wondering if, do you have a way of building in cumulative strain so that I can build a very efficient way, but it might be single use?
So what you're saying is it should be easy to use?
No, so I'm saying, can you build in cumulative strain? So for example, in airframe design,
Right.
you can build a very efficient way,
Right.
but it might be single use because the amount of strain it would be on how flights the dangerous.
Right. No, it's not single use. I mean, it's really the idea is that what is actually surprising and probably is this thing, and when you do aerodynamics or heat transfer or any of these things, seem to learn some of the physics, which means if you are doing a different object, it still works. It's not limited to a single car. It seems to learn something about cars in general.
So I was talking more about the materials. So obviously, if we have designed under a lot of strain, then that material is weakened in use.
Okay, so I'm not sure I understand the question, but if you mention strain, you're talking about structural issues, which we should also optimize for. And we're getting into another complicated problem, which is you don't typically, let's say the glider, because I understand that problem a bit better. This thing is taking incredible G loads in the turns. You don't want the wings to fold. That would be bad. So it means it has to have enough structural strength, which means you have to optimize for this as well. And what we really want to do is a Pareto optimum. You have this multiple criteria you want to optimize for. And in the end, it's the whole problem of multi-criterion, multi-physics optimization. And this is not a problem we are going to solve. Our goal here is to bring this into this area where there's all these methods and all these people working on this, and we hope they will solve it.
Thank you.
A couple of related questions on the latent representation space. So you're doing deterministic optimization, which means for the shape construction example, you arrive back at the original shape.
Mhm.
If you have a continuous path with intermediate shapes, each of which is slightly better in terms of the silhouette loss, I guess, if that's what you're using. And you don't have any path that end with degenerate shapes, which look the same but have different occluded shapes. Do you do anything to shape the structure of the latent space such that you make it easier for the optimization process later on? And when you're later on, when you're looking for knuckle shapes for different tasks, is it important when you start the process of optimization, and is it useful to inject stochasticity into the optimization process? Do you rather unusual solution?
Okay, I'm not sure I understood the question, but you said something about deterministic.
Yes, so when you're optimizing from an initial solution to a target solution, you're following a path.
Right.
You're treating your physics model or your loss as a function, and you're moving the weight space at that time.
We could randomize, of course, because we have a different function. So, for example, an algorithm that's very well known when you're optimizing non-differentiable functions is called CMES, which you throw particles around and you see where they go. There's nothing that stops us from doing this. And we're going to do it is just because we want to escape local minima. You randomly, the particles for us is the vector C. So you randomly choose vector C, and then you do gradient descent from that, and then you maybe generate new things in a semi-random way, CMES style, and then you do it again. So there is no, it's just what, I mean, there are so many things to do that we can't do them all, but what we are doing now is really simple gradient descent, but we are well aware that's not the best you could do.
Okay, thank you very much.
Okay, thank you for this info. So actually, generating objects using drawing is really very interesting, and especially as a source of synthetic training data. I'm just wondering if this approach for rigid objects also can be extended to non-rigid objects.
Yes, but yes, the close. I've shown you it's already been extended. It's the close of, oh, you were talking about the sketches.
Yes.
To be honest, I don't see why not. I mean, you could sketch, so you're now not a car designer, you're a fashion designer. And you still might want to sketch a coat or something.
Yes.
And
I mean, for example, for a car, it's relatively easy because we have some constant relation between the objects.
right, so it's more difficult, it's much more difficult for a coat. But then you have physics. So I'm not easy, but the way I would attack the problem is by saying, okay, we have some physics constraints. The code does not deform in completely random. If it can deform in completely random ways, not much we can do. But if it obeys the laws of physics, and if it's not too flexible, so it's a little bit of smoothness, then I think this will extend.
Yeah, and also another follow-up question. So when we generate the object using drawings, how can we keep track of let's say, the door concepts or the wheel concept?
The real contours?
Yeah, for example, if I would like to use this object for semantic segmentation and so on, I still need the ground truth somehow. So let's assume that I generated a human then how do I know that this is the face of the human in the object?
You solve the vision problem? No, more seriously, okay, this is not about semantic understanding of anything we know a priori. Here, I mean, as we can discuss this, but there's no, in all of what I presented today is, you know what you're looking at. And what you are being presented with is is of that type. There is no attempt at recognizing.
Last question. I have just a last night question about the construction from single image. At which level we can trust, or designer or industry application can trust in this, who just still for fun or for CVPR and BMVC conference?
Well, the reason it's being used is because we have these benchmarks, right? You can do visible reconstruction using multiple cameras, and you have the shape to arbitrary precision. And then we compare the results. So we can actually validate, which is why it's so popular, right? Not because it's useful.
Thank you. Again, Professor Kwak, this relevant